Hi everyone. Here I am talking through a screen this time. Sorry I couldn't be with you guys this last week, but we got these recordings that I'm going to be making. The way it's going to work is I'm basically going to use this PowerPoint as just a whiteboard, and so I can type equations and stuff using the built-in feature, how to do this. It's working. Yeah, there we go. So it lets you type equations and stuff, and I can do things like this. So I'll be using that to sort of type on the screen, and then I'll occasionally be drawing with my trackpad. Please bear with me when I do that because it's going to suck. My drawings are going to be really bad. But that's okay. If you have questions, please raise your hand and ask to stop the video. Right, so I'm going to leave some time at the end of this video. I think it should be about an hour long, which of course we have an hour 30 of class. So after the video finishes, you guys are expected to stay in the classroom and just kind of work on the homework. So you have extra time to work on the homework because I'm not there. But yeah, if you have questions, just stop the video and everybody sort of discuss together. So people who understand can maybe help people who don't understand or who are asking the questions. So because I'm not there, I'm gonna need all of you guys to help each other try to get the questions answered as much as possible. So you can also Slack me with any questions that you guys might have. And yeah, without further ado, the last topic that we're going to touch in this course is called resonance. And so it's a really important topic that you see everywhere in lots of different ways. And so resonance kind of has to do with, having a damped oscillator, right? So we have, maybe I'll make a little drawing of it. So just to remind you guys, you've seen this many times. What size is this? That's good. So we have a wall. Yeah, I hate drawing with a trackpad. We have a wall, we have a spring, and we have some sort of damper. Boop, boop, boop. And so the idea is, right, we know how this system behaves, right? If it's underdamped, it'll oscillate with a decaying amplitude, exponentially decaying amplitude, and we figured that out already. And if it's overdamped, it won't even oscillate, it'll just decay, basically, in amplitude. All right, but what we're going to do is we're going to take that system, we're going to add one more force to it, okay? And this force is going to be called a driving force. So this is just a time-dependent force that we apply to our mass. And I'm going to call it F, I'm going to call it FD of T. That's a D, not a knot. It's very hard to draw a D. Okay, this is the driving force. So let's write that down. Come on. Okay. We add a driving force to the oscillator. And just give me 1 second here. So it's going to have a form FD of T. So it's sort of a time-dependent, time-determined force that we're adding to our system. So we're kind of grabbing the mass and we're jiggling it back and forth. And so the way that we're going to write that is it's going to have some sort of amplitude. So this is the strength of the force. I'm going to call F naught. And it's going to be sinusoidal. So it's going to be F naught times cosine of omega t. Now, in general, I could have the phase of this force. I call this phi d or something. But what we're going to do is we're going to set set phi equals 0, phi d, I guess, for this derivation. So we could sort of shift this force left or right in time. It won't really change anything important. All that will do is sort of change our entire system left or right in time. So don't worry too much about setting this to 0. We're not losing that much. We're technically not covering as much of a possible space of behaviors if we set this to 0. but that's fine. It's actually, we're losing out on very little. It's not very deep. So this is kind of the idea. We have our mass, and we're going to start driving it with some sort of force here. So let me speak about these constants, right? F naught is the driving amplitude, and omega is the driving frequency. Okay, so these are both given, just like K and B would be given. And what we're going to be interested in is how this system responds to having different driving amplitudes. Like if we drive it with a bigger, stronger force, like the peaks and troughs are further from zero, what does that do to the system? How does it respond to that? And also we have a different omega. How is the system going to change over omega? Now F naught, the dependence on the driving amplitude, I'll just spoil it right now. It's going to be very boring. You drive it with a stronger amplitude, you drive it with a stronger force, then the amplitude of the motion will go up linearly with the force. That's kind of boring. But if you drive it with different frequencies, what we're going to find is that there's a certain frequency you can drive it at where you get really big motion. But at other frequencies, you get actually much smaller motion. Okay, so let's actually just see a video that I recorded in my room of me kind of going around. Well, I'll just let the video speak for itself. Okay, here we go.
All right, so let's do a quick demonstration of resonance. So what I've got here are my studio headphones, and studio headphones usually are built using this kind of long coily wire so that you can, use your rolling chair to move around the studio, and you don't have to unplug your headphones. It can be short if it has to be short, it can be long if it has to be long. So at the end of it, I have my LED light controller. That's how you know I'm a real Gen Z. Sort of tied to the end of this studio headphone. And yeah, I just wanted to add a little bit more mass at the end so the demonstration was more clear. So we have a spring, which by the way I can change by changing where I grab it from. It's stiffer if I grab it closer to the end, less stiff if I grab it further. We'll probably stay pretty close to this just so we avoid annoying pendulum modes and stuff like that. And damping is also here. You can tell because if I give this a jiggle, it just kind of stops, right? So clearly the system has damping in it, it loses energy, and the mass is at the bottom. So okay, let's see some resonance, right? So first off, what I'm going to do is my hand is going to act as a driving force, and I want you guys to think of the height of my hand kind of like as the force that I'm applying. It's not exactly true, but it's not totally wrong either. So for low frequencies, right, I'm going to move my hand up and down really slow, and I'm going to try to always move my hand up and down by the same amount, right? So that's how you can tell the force is the same amplitude, right? We're applying the same strength force all the time. All that we're going to change is the frequency. So for low frequencies, right, which are much lower than the resonant frequency of this guy, well, let's see what happens. So if I move my hand up and down really slowly at a low frequency, it's kind of like my hand and the mass just move together. They're completely, what you would say, in phase, right? So they both move with this sort of sine-like motion, but the peaks and the troughs, they're like right on top of each other. When one of them moves up, the other one also moves up. Now let's look at a high frequency case, right? So here I'm going to do a really high frequency. It's very hard to do this without exciting other modes. There we go. So here's a really high frequency oscillation, and you can basically see it's not really moving too much. It's actually very hard to see in the system because I'm activating a lot of other modes, but what you should be seeing is that as my hand moves down, the mass is actually moving up. And when my hand is moving up, the mass is moving down. So they're kind of in anti-phase. Remember, low phase, they move together. Low frequency, they move together. High frequency, they move opposite each other. So at resonance, you're actually going to have a 90-degree phase shift, right? So that means it's kind of in between those two. It's kind of like if the force is a sine wave, then if the force is a cosine wave, then the motion is going to be a sine wave. Just the same thing, but shifted by 90 degrees. So let's try to see that. I'm going to start at a very slow frequency. And as I speed my hand up, we're going to go over a period of resonance. It's coming. There it is. And you can see that my hand is still moving just as much as it did before, but now the mass, it's like really jumping around. In fact, so much so that it starts picking up all these other modes like pendulum motion and stuff. Okay, yeah. So actually the spring becomes very non-linear. We're no longer in the linear Hooke-Slaw regime of the spring, but still, yeah, so you guys can see that's what resonance is, right? There's a certain frequency that I can drive it at where it just kind of like sends a lot of energy through compared to other frequencies. And if I keep going to higher and higher frequencies, it kind of slows down. It stops picking up as much energy. Let's bring it back down to resonance. There it is. So it just starts going all over the place because it's a really bad oscillator. But hopefully that gives you guys an idea of what's going on. And the key here is notice in phase at low frequencies, opposite phase at high frequencies, okay?
All right, so that demonstration was okay. You could see the low frequency case very well, but the high frequency case was kind of difficult to see. So why don't we go online and let's see. Let's look at, I should have this saved somewhere here. This is a really good website I can share with you guys that has a ton of really good physics simulations. And it has this one, which you guys have seen before in class, where you just kind of have a harmonic oscillator and you can drive it with a force, or you can just kind of let it do its thing. I'm going to increase the damping a little bit. Okay, so this is an underdamped oscillator. You can tell because it oscillates and the amplitude goes down, rather than it just being like it just goes down without oscillating. So we're now applying no force. So if I disturb it, it's just going to do underdamped oscillation. We can start applying a force. So we'll say we want the force to be a sine wave, and there it is. And it's going to do some weird stuff at first, but then eventually over time, it looks like the motion just becomes a sine wave. So the red curve here corresponds to the force, and the white curve corresponds to the motion of the oscillator. And you can see they're basically just the same thing. They're on top of each other, right? So if I instead go to a really high frequency force, then if you look carefully, you might be able to see that the white peaks are at the red troughs and the red peaks are at the white troughs. So they're in antiphase right now, right? But if we go in between, you can see, first of all, notice that the amplitude of the white of the motion is going up, right? So the amplitude of the white curve is moving up. It's getting bigger and bigger and bigger. And there's this one frequency that it just loves. It just like explodes at this one frequency. This is kind of what you were seeing in the video. At the resonant frequency, it just completely explodes, right? This is called the resonant frequency of this system. So if the driving force is at that frequency, then it'll oscillate really strongly. It'll respond very strongly. And if we go back below it, you can see it kind of starts dying out again. More and more and more. And the sine waves become the same once again. Yeah. So, okay, let's write the system down. I think we can write this down at least to start. So we know that we have we're going to use F equals MA, right? So we have MA equals, we have the spring, that's minus KX. We have the damper, that's minus BV. And we're also going to have this driving force. So it's going to be F naught cosine of omega t, okay? Everything here is given. The only things we don't know are V, X, and A, which are really just derivatives of each other. But everything else is like a given constant. We don't, don't be confused with like when we make an ansatz and we have a bunch of constants we don't know, we have to find. Everything here is known so far, right? Okay, so if we have this, we can rewrite this as X double dot, let's see, plus 2 gamma X dot plus omega naught squared X equals F naught, little f naught, cosine of omega t. Okay, what are all these constants I wrote down? So a lot of them you should recognize already because we used them previously. So gamma is just b over 2m. Omega naught squared was, or actually just omega naught, let's say. Omega naught is just square root of k over m. And little f naught is the driving amplitude divided by the mass, right? So these are the three sort of constants that we have here. So this is the differential equation we have to solve now. So we have a function, we have its derivative and its second derivative. They're added together with some constants in front. And that whole sum, before it was equal to 0, now it's equal to this f naught cosine of omega t. It's equal to a function of time. Okay, so how could we ever make this work? Oh, and I need to plug my computer. Give me 1 second. So, well, let's think about this. We could be inspired by what we saw in the simulation over here, right? Notice that the motion is always at the same frequency as the driving force, right? Before, when we did the undamped oscillator, the frequency was set, right? And when we did the damped oscillator, when it was underdamped, that was also, it just had one frequency, you know, it would decay, whatever, but like the frequency was set by the parameters of the system. Here, the frequency is always whatever we're driving it at, right? So notice from experiments / simulations, the frequency of the motion is always omega. Okay? Always omega. It's always whatever we're driving it at. Whereas before, it depended on K, M, and B. Now it doesn't. All right. So, okay, well, that means that our gas is going to be some sort of sine function, and we're going to have omega in there as the frequency. But also notice from our simulations, we notice that the wave is not completely on top of the driving force, right? For low frequencies, it's kind of the same thing, but for high frequencies, actually, it's opposite, right? So there's a phase shift that depends on the driving frequency in some way. And so we have to kind of have this, I have to allow for there to be a different phase between the force and the motion. So our ansatz will be x of t is a cosine of omega t, right? It has to have the same frequency. And we're going to have some phase shift, plus phi. Okay. So this is exactly the same guess, by the way, that we had for this simple harmonic oscillator. Just keep that in mind. And also keep in mind that this, right, this simple single cosine, this is never going to capture, like, if I grab this and I throw it, look at all that weird non-cosine motion that it has at the beginning. Clearly, this solution is not going to be complete, but this is going to be what's called a steady state solution, right? So after all those initial things go away, you're left with this very simple cosine motion. And that's what we're going to solve for first, and then we're going to talk about how we can add all that complicated stuff at the beginning back in, okay? But yeah, so let me just say that. Note, this gas does not account for weird, what's called transient motion at the beginning. Transient because it goes away. All right. I'm going to keep that equation. So let's actually try. We have the equation there. And we have our ansatz is x of t equals a cosine of omega t. So let's plug in. Let's plug in. So remember, oh, omega t plus phi, my bad. Remember, we have to find a and we have to find phi. These are two unknown constants, and we're going to try to find them by plugging this guess in to figure out what's going on here. And what we expect to see, by the way, from the simulation, we expect a to be some function of omega, right? So if we drive it at the right frequency, then a is going to be much bigger. And phi, likewise, we also expect this to be some sort of function of omega. So, okay, let's do this. All right. So, just looking at my notes real quick. All right, let's get the derivatives first. And I won't do the whole procedure. You guys are going to have this on your problem set. And it's kind of annoying. So, but a is a constant, so it just hangs out as we take derivative. Okay, wait, no, I need to take the derivative, my bad. X dot of t is going to be a times cosine of omega t plus phi. And I forgot there's an omega now, and it's not a cosine, so this is just completely wrong. Omega, there's a minus sign now, right, because we took the derivative. My bad. Okay. And we're going to have x double dot of t is going to be minus omega squared a cosine of omega t plus phi. Okay. And now if we throw those in there, we're going to get the following equation, right? We're going to get, let's see. Yeah, okay, we're going to get minus omega squared a cosine of omega t plus phi. That's the x double dot term plus 2 gamma, and it's going to be minus in the end, 2 gamma. And then we have the x dot term, so that's omega a sine of omega t plus phi. And then we're going to have plus omega naught squared a cosine phi. And all of this is equal to f naught cosine of omega d. Okay, all right. All we did was plug in. So, by the way, the general procedure when you plug into differential equations and then you want to solve for your constants or whatever is you have to look for functional dependence, right? So how does our equation depend on time? And there's going to be a couple of different ways. So what we're going to do is we're going to write this so that we have cosines of omega t only without the plus phi and cosines of sine of t only without the plus phi. Right? So we kind of want those two types of functional dependence, right? So ways that things can depend on t. There's a cosine or a sine. And then we're going to group all those together. And then we're going to say the coefficients to each of these have to be 0. So what am I saying? Approach, set coefficients to all types of functional dependence on t to 0. So that's going to look like we're going to try to transform what we have over here into something of the form, something here times cosine of omega t plus something here times sine of omega t equals 0, right? So this equation that we have here can be written in this way, right? How do we do it? Well, you have to use this sort of sum angle identities using cosine of omega t plus phi is going to be cosine of omega t cosine of phi minus sine omega t sine phi. And likewise, there's also one, I'm going to make this a little bit smaller so it fits. And likewise, there's also one for sine. So why would you make it bigger again? So for sine, it goes sine of omega t plus phi. Oh, come on. Is going to be cosine omega t sine phi. And it's going to be plus sine omega t cosine phi. Whatever. I don't care. Okay. All right. Oops. Sorry, guys. All right. So that's the approach, right? And using these things, we're going to get two equations that we can use to solve for A and for phi. Remember, that's what we're trying to do at the end of the day. We're going to get that the stuff in the first parenthesis, is going to be equal to 0, and the stuff in the second parenthesis is going to be equal to 0. Okay? So by parenthesis sub 1, I just mean whatever's next to the cosine. Parenthesis sub 2 is whatever's next to the sine. This is the approach, okay? I'm not going to do it here live because that would be awful for you guys and for myself. I hate working on this PowerPoint and doing math via PowerPoint. So I'm just going to give you guys what the answer looks like. You guys have to work through this in your problem set, but hopefully you have enough instructions to figure out how this all works. Yes. So what will this give? This will give us, again, like I said, it's going to give us two equations in the end. One thing equals 0 and the second thing equals 0. So the two equations are going to be omega squared minus omega naught squared cosine phi plus 2 gamma omega sine of phi, and I'll put parentheses here as well, just for consistency. Plus f naught over a equals 0. That's one equation. And the other one's going to be, you know what, just copy paste it. It's going to be kind of similar. It's going to be the same thing without this f naught over a term. And this is going to go here. And this is going to go there. Here. These are our two equations. So go ahead, write those down. So remember, everything here is known. Omega is known, omega naught is known, gamma is known, f naught is known, except for phi and a. We have two equations and two unknowns, so we're good. We can solve for them, at least in principle, right? Remember, what is phi? What is a? we guessed that our motion is a cosine of omega t plus phi. So we have some unknown amplitude, and phi is also unknown, right? But we know omega t, omega is just a driving frequency, okay? So we have to use these two equations to solve for a and phi. All right. This is also kind of an annoying process. Let me pause and debate if I want to do this on video. Okay, so the video is on pause now. And full disclosure, I actually recorded this entire thing while I was working on it. But after I paused the audio right there, it just stopped recording. Like it didn't go back, even though I hit record again. Anyway, so this is now a voiceover for the rest of the video. So the video was recorded before, and now I'm just talking over it. Yeah, I decided I was gonna solve it for you guys. So basically, we have to find phi and a, and the first thing that we do is using the bottom equation. There's no a in there, so we can just use it to find phi. Okay, and so I just copied the bottom equation, and the only thing I did in that step there that I just wrote is I divided both sides of the equation by cosine of phi. So the cosine goes away, the sine turns into a tangent, and the zero stays the same, right? And so from there, I can then solve for tangent of phi, which is what I'm doing over here. I just end up having a minus 2 gamma omega divided by omega squared minus omega naught squared. And so that's it. That's how we find phi, basically. We can take the arctangent if we wanted to, but that's phi. And so actually, this is something I didn't mention in the original video, but if you study how phi depends on omega, if omega is 0, so if it's really low, then you actually get that phi is 0. So that means that if phi is 0, that means that the waves are in phase with each other. So the motion and the force are going to be in phase. But if phi goes to infinity, then, if omega goes to infinity, then tangent phi has to be pi for this equation to work, which would mean that they're in antiphase with each other, which is exactly what we saw in the experiment. So this confirms what we saw in the experiment in terms of the phase between the motion and the driving force. Because remember, that's what phi is. It's the phase between those two waves. So now we want to find a, and so we're going to use the top equation because now we already have phi, so we can use it in that equation there. And so what I do is I believe I solve for a at this point in terms of like phi. So yeah, what do I do here? Yes, so I basically multiply both sides by a. So that term turns into an f naught, and everything else just has an a multiplied by it. So I'm adding some square brackets, and there's an a in front of everything else. I just multiplied the equation by a. And then, of course, I can solve for a by just dividing by that whole square bracket. And it gives me minus f naught divided by, and then there's that whole thing down there. There's a sign error that I catch later, so I'll tell you guys about it when I see it. But basically, the cosine should have a minus sign. But anyway, okay. So yeah, so now I'm solving for a. So the only thing we have to do now is find what cosine phi and sine phi are. But we know what tangent phi is, right? So we can use that to find cosine phi and sine phi. Yeah, so now we want to plug in for cosine phi. And sine phi. Man, doing a voiceover is so weird. Okay, so we know that tangent phi is that, and we know that, so I think I'm going to draw a little triangle, which will help explain this. We did this before in class, but we're just going to do it again here. So there we go. Draw a triangle, right triangle, and let's say phi is in one of those corners. So if we know that that angle is phi, then opposite over adjacent must be tangent of phi. So in order to get what we found over there, then the opposite, we can write the opposite as minus 2 gamma omega, and the adjacent as omega squared minus omega naught squared. That's what I'm going to do, and that's what I'm probably talking about there. Minus 2 gamma omega, and I'm writing it very slowly because I'm using my mouse. It's awful. Okay, you guys get the point. And then with that, you can find the hypotenuse, right? Which if you want to find sine or cosine, you're going to need to do opposite over hypotenuse or adjacent over hypotenuse. So we need the hypotenuse to figure out the rest. So here I decide I don't want to write out the hypotenuse using the red pen because that would be a pain. So instead I'm just going to type it out and then put that in the hypotenuse up there. So it's just the adjacent side squared. So that's omega squared minus omega naught squared squared. There's that final square. Plus the opposite side squared. 4 gamma squared omega squared. There we go. And then I just put that as the hypotenuse because I didn't want to deal with that. There we go. So using that full triangle, we can now find what sine theta, what sine phi and cosine phi are. Sine phi is just going to be opposite over hypotenuse, which will be minus 2 gamma omega over the whole hypotenuse thing, which I just pasted there. And cosine phi will be the adjacent over the hypotenuse. Without the minus sign. There it is. So now we have sine phi, cosine phi. We can plug those in to find A, basically, which is what we were trying to do this whole time. And I think here I'm taking a sip of my coffee, giving you guys time to write down those equations. Man, this is weird. Okay. All right, so now we're just going to plug into A to get the final value of A. And I'm just jotting down all those equations from earlier. So we have them all in one place. There's A, there's the cosine phi, and there's the sine phi. And so what I'm going to do now is, you notice how in the denominator of A, we have omega squared minus omega naught squared times cosine, right? And so I'm just going to figure out what that term is instead of just the cosine. So I'm just going to take the cosine expression and multiply it by omega squared minus omega naught squared. Because I just want to plug directly for all of that stuff. I don't want to plug in just cosine. I just want to get rid of that whole term. So let's just see what it is. And if I multiply the cosine that we found earlier by omega squared minus omega naught squared, it just squares the numerator basically, because that's exactly what the numerator already was. And down there, right, for the sine, I do the same thing. If I do 2 gamma omega times sine, which is what shows up in the denominator of a, then that's just going to square the numerator of this expression here. Yeah. So I'm saying there we have the expressions for those two terms. So I think around here, I noticed that there was a sign error, and I went back and I found it and I paused the video, and I noticed that, yeah, if you go back to that point where we had those two equations, I wrote one of them wrong, actually. I did the math wrong. So that second equation there should have, no, the first equation should have a minus sign next to the cosine. So that correction, you have to add that everywhere, so just add it with me. So add it to that equation there. The whole derivation for tangent phi, nothing happens there because that goes from the second equation. But then for finding a, where you use that first equation, you have to add that minus sign everywhere. So make sure you guys follow that. Wherever there's a cosine, you have to basically add a minus sign as well. It just follows the cosine around. So yeah, there will be a minus sign there too. And that all stays the same. The triangle stuff we did stays the same. The sine and the cosine that we found stay the same. So then if we want to add that minus sign further ahead, we put it over here. Minus sign there. And there's a minus sign there where I'm writing out that term in the denominator, basically. Yep, one there. And I just put it in front of everything, I think. There. Okay. Yes, so now we can take those two expressions and we can plug them into the expression for a, right? So there's a. That minus omega squared, omega naught squared, minus omega naught squared cosine phi, we can replace, or I guess I'm doing the sine one first. Okay. Yeah. So we're taking the sine term, we're replacing it with that. And we're taking the cosine term and we're replacing it with that. Okay, and then I'm just, because it's way too wide, I'm basically, because they have the same denominator, you can add the two fractions together into one thing. And you get that expression. Now those two minus signs in the front of a and also in the denominator of a, those can cancel. And I think what I'm saying here is that you have, you're taking something and you're dividing it by its square root. So that's equal to just the square root of that thing, right? And I think I write it down here now. Yeah, if you have a number divided by its square root, obviously you guys know that's just going to be the square root of a, and that's exactly what's happening in the denominator of a. So there's the expression for a. It all just becomes the square root of that thing, and the minus signs basically cancel. That cancels with that. And I can get rid of those parentheses as well. There we go. And that's our final expression for A, basically. So we just found the amplitude. As you change the driving frequency, you get all these different amplitudes from your system, basically responding to your different driving frequencies. So here I'm just boxing it like I did with phi, because that's our other result. And this is basically resonance. Like this equation we just derived is basically the most important one in resonance. It shows you that there's a certain amplitude where you get the strongest possible resonance. Or the strongest possible, there's a certain frequency you can drive it at, my bad, where you get the strongest amplitude motion. So here I'm just summarizing everything we found. When you have driven harmonic motion, it looks like A cosine omega t plus phi, where A is what we just found. And phi is that other expression we had from earlier. And instead of writing phi, actually write tangent phi. So notice in simple harmonic oscillation, cosine, we had A cosine omega t plus phi, but it was different. A was determined by initial conditions, and phi was just also determined by initial conditions. Here, there's no room for initial conditions right now. Like A and phi are fixed given the driving frequency. Okay, initial conditions we'll deal with later when we add basically transient behavior at the beginning of the solution. Because you know how it doesn't always behave like a sine wave. At the beginning, it actually had some really weird non-sine wave-like behavior, as we saw. But okay, so what I'm going to do now is basically go to Desmos and show you guys what this looks like. So I think I open up Desmos. I think I'm just talking about the solution there. That's my paper. Okay, there's Desmos. Okay. So here I'm writing the expression for A that we found, and we're going to start looking at it a little bit so we can sort of see the behavior of resonance. So we found that A was F naught divided by the square root of omega naught squared minus omega squared minus omega naught squared, all squared, plus 4 gamma squared omega squared. We want to see how this amplitude changes as a function of omega. And so there it is. Now the first thing I think I do, well, okay, I guess I start changing my parameters and we can see how this responds. So in reality, the x-axis should only be defined for positive omega because a negative driving frequency doesn't really mean anything different because it's in a cosine, a negative driving frequency is the same as a positive one. So we only care about the positive ones anyway. That's what I did there. And so you can see that there's a certain frequency at which we get the most amplitude in our motion, right? Now, that frequency is pretty close to omega naught. Omega naught, remember, is the undamped frequency of oscillation. Like if you just had a spring and a mass, it would oscillate at omega naught. But it's not exactly omega naught, because there I mark omega naught on the graph. And you can see that it's not really at the peak. So the resonant frequency, right, that maximizes this curve is not at the undamped frequency. So maybe it's at the damped frequency, right? Because if you remember when we did the damped oscillator, we had a frequency, when you had the underdamped case, It was omega naught squared minus gamma squared. That was the frequency. And so I'm checking to see if that's at the peak. But you see that it isn't really. It's just to the right of the peak. It's a little bit too high. So this resonant frequency isn't any of the other frequencies that we found so far. It's something else. So that's kind of curious. Right? So there's a resonant frequency which is not either of these guys that we've already encountered. So I ask you guys, like, how would you find this resonant frequency? Right? How would you do it? Well, you'd have to take the, right? You have to use calculus to find the peak of this curve. And so that's what you guys are going to do in like a second, I think. Here I'm going to basically write down what I was just voicing right now. So omega naught is the undamped frequency, which corresponds to the frequency of just the spring in a mass, which is just square root of k over m, if you remember. So there I'm changing the colors of everything. So blue is undamped and green is underdamped. So there is damping, but it's not as strong as the, as the thing, as omega naught, sorry. So now I'm talking about the underdamped frequency. Right, omega naught squared minus gamma squared, that was the frequency that an underdamped oscillator would oscillate at when you had some damping but not enough to overcome omega naught. There, gamma is less than omega naught. That's the underdamped condition. Neither of these are the frequency which maximizes the amplitude, or the response. You can also call it the response. Yeah. That frequency is called the resonant frequency of the system. So yeah, it's whatever frequency maximizes, gives us the peak value there, that number. You can see it's neither the blue nor the green dot. So what I'm going to ask you guys to do now is take 10 minutes to find that frequency yourselves. It should just be a maximization problem using calculus, okay? So I think here I'm just sort of showing how no matter what I do, that's always a different number from the other two frequencies that we've encountered so far. So I'm showing F naught just changes, it's just multiplying everything, moves things up and down. If I change omega naught, it kind of moves things left and right. And also kind of splashes it out. And you guys can code this up yourself. You saw what I did in Desmos, so it's actually very, very easy and very fun to play with. And if I make the damping bigger, it kind of flattens out this curve. And there's Marcus sending me a message. And yeah, if you decrease the damping, then you can see that the response kind of blows up. But also the width of this peak becomes thinner and thinner, right? So when you have really low damping, that's called a really high quality curve, where you have to get the frequency just right. But if you get it just right, you're going to get a really high amplitude response. That's what a high quality oscillator is. So there I'm trying to show you what happens if I take the damping to be very close to 0. Yeah, you can see the whole thing just explodes. And actually, if you set it to 0, it literally explodes to infinity. But I'm showing that even in this case, the resonant frequency is still different from the other two frequencies. Notice how the undamped blue and the underdamped green frequencies are not quite at the peak. They're still not equal to the resonant frequency. So yeah, so now I'm going to pause for 10 minutes and then we'll come back. But I'll go ahead and pause the video and you guys just have to find the value of that resonant frequency by maximizing the A of omega function. Okay, so 5 to 10 minutes, whatever it takes. You guys can figure this out and we'll come back. Okay, I think this is me coming back. So what you should have found was that omega r, the frequency that maximizes the response, was omega naught squared minus 2 times gamma squared. So it's very similar to the underdamped frequency, but it's actually a little bit lower, which is, it's good. That's what we've been seeing. So if we go back to the Desmos and we plug that in, which I already did there while the video was paused, you can see that that's exactly at the peak. And here I'm just changing the color. I'm going to change it to red. Make the point a little bit bigger. And I'll turn off the other two. And you guys can see how the peak of that curve is always the red point that we just found. Now what can happen, you can see there's some parameters where the peak is to the left of 0. And so there isn't really a peak, right? So it's possible that there is no resonant frequency. The amplitude just goes up and up and up as you keep decreasing the driving frequency. That happens when you have really strong damping. And it corresponds to when that square root of omega naught squared minus 2 gamma squared is negative, right? Because then you have an imaginary value there and there's no real solution to that. But it should be clear to, like, I should clearly note to you guys that even though the resonant frequency goes away, the solution to the motion is still the same. Whereas in the underdamped oscillator on its own, the solution totally changed from like sinusoidal oscillating to exponential decaying. In this case, the solution stays the same. It's always just a sinusoidal oscillator. So what we're showing you now is a video of something called the Tacoma Bridge, which I'm just kind of playing from the beginning-ish. And this is a video that is shown to everybody as they are learning these topics. It's kind of like a rite of passage for physicists and engineers to be shown this video, even though it's actually not really that adequate. So I just felt like I had to show it to you guys, right? So there was this bridge that was built somewhere in Washington. I don't, was it Washington? Was it Washington, D.C. or Washington, the other one? I don't know. But there's a bridge somewhere. There was a bridge, Tacoma Narrows Bridge. And this is shown as a classic example of resonance occurring, right? So let's see here. Basically what happened was the wind was blowing at, and they say this in the video, the wind was blowing at a steady 42 miles per hour. And somehow it made their bridge do a little dance, which is kind of insane to think that the concrete and the asphalt and all these things can even bend like that. And so, yeah, you guys can look up this video, by the way. It's very easy to find. Just look up Tacoma Narrows Bridge. And so this is kind of showing, it's supposed to be showing the effects of resonance, right? That if you're driving something at just the right amplitude, you can make it oscillate really hard. And actually here you have a guy walking, you can maybe barely see them. They're walking on the center line of this oscillating bridge, kind of down that yellow line. There was an engineer that apparently decided it was a good idea to go there and check what was going on. Nobody was killed except a small Cocker Spaniel, a dog that was stuck in that car you see there, which is very sad. Apparently that engineer that was walking on the bridge for some reason decided to try to save the dog, but the dog bit him because he was really scared. So it's kind of sad. But yeah, so what's really happening here, right, is a very complicated interaction between the wind and the angle of the road. So as the angle of the road changes, there's kind of this feedback loop that makes it oscillate harder and harder. But it's not really that the wind was an oscillating force. The wind is actually pretty steady. It's just this kind of feedback loop. So it's not really resonance. There's just this feedback loop between the angle of the road and the wind, and they kind of like build on each other. And there's some aerodynamic effects at play here, which I think I'm going to talk about at the end of this video. But you can see this does not look safe. This was not safe. So you guys have to be very familiar with this if you're going to build any bridges, please. And then there's just this quick clip of the whole bridge falling. So apparently it was doing that dance for like an hour until it finally fell. So yeah, people don't make that mistake anymore. But everybody sees this video at least once in their STEM career. I swear to God, they showed this to me twice, 2 different classes. It's just like a famous example of resonance. You'll always hear about the bridge in your classes. And so here I sort of look up something called vortex shedding, which is part of the explanation for what happened here, but I hear that it's not actually the correct explanation for what happened. I don't know. It's like a whole thing. Like people say this is an example of resonance, but in reality it isn't. But it is a cool video to show your students and make them be impressed about how applicable what you're doing is. So I guess that's what we're doing here. Yeah, so this is vortex shedding. If you imagine you have wind coming from the left and you have a circular like chimney, then the wind will do something like this. It'll start shedding vortices. And you can imagine if you're doing this, that it's kind of, if the wind is being pushed left and right, then by the equal and opposite Newtonian force, the chimney is being pushed right and left. And so there's this oscillating push on the chimney. But it turns out that if you calculate the frequency of vortex shedding for that bridge, it does not match the resonant frequency that we were seeing in the video, which was about 0.2 hertz in the video. So it doesn't make sense. That's not the right explanation. It's something related to vortex shedding plus other stuff going on. I don't remember. There's like a little paper you can look up that tries to explain what was actually going on. But it really wasn't resonance. People say it is, and it's like the classic example, but it really wasn't. So anyway, this is what I had to show you guys today. Next time we're going to do the same derivation, but we're going to do it with complex numbers, okay? And so that in the final, you guys will get to choose between using complex numbers for a derivation or using real numbers for a derivation. So instead of me forcing you to do it one way or another, you guys will get to choose. But in the homework, you guys have to practice both. So if you have any leftover time, please just spend it doing the homework or asking questions and stuff. And otherwise, I'll see you guys on Wednesday, or this recording of me will see you on Wednesday, and we can cover how to do the same procedure with complex numbers. So I'll see you guys then.